In a previous video, we were discussing the different types of number systems. And at some point I mentioned the word field. But what is a field? So let us define it carefully now. So definition, a field, let's call it F, is a set with two operations that we denote addition and multiplication, but this is just a symbol. It's not necessarily the addition we are used to, okay? Or the multiplication we are used to. This is a set F with two operations defined on it, which satisfy the following axioms. Okay, so let me create more space here. A field has 10 axioms. Actually 11. So let's start with the axioms for addition. Axioms for addition, we have 5 of these. So we have A1. A1 says that the sum is closed. Closed means that whenever we take x in F and y in F, x and y elements of F, then the sum x plus y is an element of F. Okay, so you take two elements of the set, the sum is on the set. That means being closed by the operation. The second one is that the sum is commutative. Let me just write commutative. Okay, so what does commutative mean? Commutative means that if I take x plus y, that is the same as taking y plus x. Okay, and this is for all x, y in F. Now, the third axiom is the associative property. Okay, this means if I do x plus y plus z, this is the same as doing x plus parentheses y plus z. So when I adapt 3 elements, it doesn't matter, you see, because the operation is defined for 2 elements. So I can do first x plus y, or I can do first y plus z. And then when I add the third element, it's going to get the same result. Okay, this is for all x, y, z in F. Okay, so that's the associative property. Then we have the identity. This means that there is an element, F contains an element that we call 0, but this is just a name at this point. Doesn't necessarily mean the 0 we are used to. Okay, but it has to satisfy this property such that 0 plus x equal x plus 0 equal x for all x in F. Okay, and then the fifth is the existence of the inverse. Okay, so if you take an element x in F, then there is an element y in F such that x plus y equals 0. Okay. Now, we don't really write y here. We call it minus x. Okay, so x plus minus x equals 0. That's how we denote the inverse usually, okay? So these are the axioms for the addition, okay? Closed, commutative, associative, identity, and existence of the inverses. And for the multiplication, we have similar axioms. There are 5 more axioms for multiplication. They are the same axioms, just written for the multiplication. So let me just copy paste. I already wrote them down, so we can go over them together now. So the axioms for multiplication, we have that the multiplication is closed. That means that given 2 elements of F, the product is in F, okay? It is commutative. So x times y equals y times x for any xy in F, okay? Associative. So if we have 3 elements, x, y, and z, we can multiply first x and y or first y and z, and the result is going to be the same. The parentheses always express priority. There is the identity element. In this case, we call it 1, even if it doesn't have to be, I insist, the number 1 we are used to. And this is different from the addition identity, okay, which is the 0. This number 1, or well, this element 1, actually, not number, sorry. When we multiply by x, or from either side, we get back the original x. Okay, this is true for every x in F. And then we have the existence of inverses that are special numbers, such that when we multiply x by its inverse, we get the identity. We get 1. Okay, we denote 1 over x just out of habit. Okay, it's a traditional notation. And then there is one more axiom that is called D, that is called the distributive law. Okay, and that connects the 2 operations. Did you notice that so far we have 2 operations that they are not related, but the distributive law is going to do that job. So it says that when we multiply x times y plus z, the product distributes. So it's x times y plus x times z. Okay, and this is for all x, y, z in F. Again, we are used to these things, so we take them for granted, right? The point here is that there are so many more sets that satisfy these actions for different operations, okay? And it is useful to study all of them at once. It's very similar to when in linear algebra we start studying abstract vector spaces, just because we realize that there is a common structure and we can do all of them at once. Okay, of the examples we have seen so far, the set of rational numbers is a field with the usual addition and multiplication. Okay. Here, I will leave this as an exercise for you to check all these 11 axioms, check them one by one, and see that actually they hold. Okay. Then there are some I mean, any familiar properties of the rationals are consequences of these field axioms. Okay, so for example, let me show, let's say the cancellation law. In the rational numbers. Okay, here the nice thing is once we learn to do it for rational numbers using the field axioms, then we can do it for the reals, for the complex numbers. It's the same proof. So once you learn to do it for one field, you can do it for any field. So the cancellation law says that x plus y equals x plus z. If we have an equation like this, then what? Then y must be equal to z. Okay, we can cancel the x's. And this is obvious with numbers. We do it all the time, but we need to prove it using only the axioms of field. So the axioms because here we have only additions, we need to use the axioms for the addition, right? And we can write it like this. We can say, well, y equals 0 plus y, right? This is the A4. Then I can write 0 as the inverse of x plus x. Right, so this was A4. The inverse of x plus x equals 0, that's A5. Okay. Here you notice we have 3 elements and we have a parenthesis, so we can use the associative. So it's A3. So this is going to be negative x plus y. Okay. Now, because I know we have this identity, this is our hypothesis. Actually, instead of a star, let me just highlight it with a color. Okay, here we can use that this is equal to negative x plus, and here we use the hypothesis plus x plus z, okay? And we keep moving. So now we have here again 3 numbers. We can use the associative property. That's A3. Okay, so A3 says we can move the parentheses, and we have here property A5, the inverse, okay, gives 0 plus z, and this is A4. This means the identity says this is equal to z. So you see what happened here? We look at the beginning, we have y, and then equals to z. We have used only the axioms of field. So this is the way you prove any property that you want using the axioms of field. And a computer can do this, okay? Just follow the logic and do steps that for us may be obvious because we are used to them. But we need to make sure we are not using anything outside of the definition of field.